We will now see a nice application of the uniform boundedness principle or Banach-Steinhaus theorem. So we are going to see an application to Fourier series. So let f from minus pi to r be an integrable function. So we write its formal Fourier series . So this is f of t is sigma n equals minus infinity to infinity f hat n e power I n t. So we are writing it in the exponential form. This tilde here just shows that this is a formal series. We will discuss when it should we write an equality. So f hat n, these are the Fourier coefficients. This is 1 by 2 pi integral minus pi to pi f of s e power minus ins ds. Okay, so these are called the Fourier coefficients. Okay, so the question which we are going to ask is, to what extent does this Fourier series represent the function itself? In particular, for instance, if f is a continuous 2 pi periodic function, that means it takes the same value at minus pi and plus pi, will the Fourier series converge to f of t at every point t in the interval minus pi to pi? So this is relevant since each term in this series e power I n t is cos n t plus I times I n t, and therefore a 2 pi periodic function. So we would like to know if this is so. Unfortunately, the answer is no, and it was a big controversy in the latter half of the 18th century. For nearly 70 years there was this controversy, till in the beginning of the 19th century Dirichlet established in 1829 the first sufficient condition for the series to converge to the value of the function, or to whatever it converges to, and then it was strengthened by Jordan. And in fact, the study of Fourier series, justification of its convergence and all this led to a lot of mathematical development, and like making precise what is the notion of a function, what is Cantor's theory of infinite series, the theories of integration of Riemann and Lebesgue, and the theories of summability of series. And all this led to a lot of research, a lot of mathematics got developed in just trying to understand what this means. In this talk, we will now use the Banach-Steinhaus theorem to show that there exists a very large class of continuous 2 pi periodic functions where the Fourier series will fail to converge, and the set of points where it converges is also very big. Okay, so that means the situation is quite bad, and therefore one has to see in what sense we want to use the Fourier series or not. So what do we do to study the Fourier series? So we have to study the convergence of the partial sums, which is SMF at t, which is equal to sigma n equals minus m to m f hat n e power I n t. So these are the partial sums of the Fourier series. And if you use the formula for the Fourier coefficients, which is f hat n is given just above, then this becomes Sm f of t will be equal to sigma 1 by 2 pi integral minus pi to pi fs dm t minus s ds, where dmt equals sigma n equals minus m to m of e power int. Okay, so this just you substitute and you get this formula. So we have to look at this function, and in particular we have to look at this function dmt. This is called the Dirichlet kernel. And the first thing is it's an even function. dmt equals dm of minus t. So it's an even function. Okay. Okay. Now you multiply this dmt by e power it by 2, multiply it by e power minus it by 2, multiply this, subtract, and then lot of terms will, it will telescope, lot of terms will get cancelled, and finally you can show the following thing. So this is just calculation and I am not going to do that calculation. dmt is equal to sine m plus half t by sine half t if t is not equal to 2k pi, k non-negative integer, k integer, let us, because dmt is dm minus t, it does not matter. Then it is 2m plus 1 if it is t is equal to 2k pi. Okay. So the first proposition is that limit n tending to infinity integral minus pi to pi dmt dn of t, let's say, modulus dt is in fact plus infinity. Okay, this is not very difficult to do. So proof, if we have that mod sin t is less than or equal to mod t, this we know for the sine function. Okay, so integral minus pi to pi mod dnt dt is bigger than or equal to integral, first of all I will write 2 times integral minus pi to pi can be written as twice integral 0 to pi, because we are having an even function, and then you have mod sine n plus half t, and in denominator mod sine t by 2 I am going to write is less than or equal to t by 2, so that will be greater than or equal to 2 by t, so mod greater than t, there is a 2 here, and then already a 2 because I made the integral half range, so this becomes 4 times integral 0 to pi sine n plus half t by t dt, and that is if I make a change of variable, so this will become 4 times integral 0 to n plus half pi mod sine t by t dt. Okay, so make a change of variable, you will automatically get this. Now that I am going to split this gradient equal to 4 times integral sigma k equals 1 to n integral k minus 1 pi to k pi mod sine t by t. Okay. Now why greater than or equal to? Because I only went up to n pi, the integral is actually up to n plus half pi, so I have left out some portion and therefore I have to put a greater than or equal to sign. Now here we are going to write this is bigger than or equal to 4 times sigma k equals 1 to n integral k minus 1 pi to k pi of mod sin t, and denominator t is less than k pi, so denominator it is bigger than k pi. So in 1 by t is bigger than 1 by k pi, so I can write this, and that in fact is equal to 8 by pi sigma k equals 1 to n 1 by k. Okay, so this is this straightforward integration of mod sin t, and therefore you get this 1 by k. Now sigma 1 by k, you know, is a divergent series, and therefore these partial sums will go to infinity. Integral is bigger than or equal to this, and that proves that limit of integral minus pi to pi of dnt dt is plus infinity. Okay, so that proves this proposition. So the next proposition, so we are going to take V equals C periodic minus pi pi. So this is what? This is the space of continuous 2 pi periodic functions. So this is a vector space, and then you are going to put the usual norm. So norm here is the sup norm as usual, and that I am going to call it as norm infinity. Okay. Now define phi n from V to R. So phi n acting on any f is nothing but Sn of f. So Sn of f is the partial sum of the Fourier series, that is a function, so I am going to just evaluate it at 0. Okay. Then phi n belongs to V star, it's a continuous linear functional, and we can actually compute its norm. Norm of phi n is equal to 1 over 2 pi integral 0 to minus pi to pi mod dnt dt. So that is why we calculated that integral a little earlier, because this is in fact the norm. So proof: on one hand, what do you have? So we have phi n of f is 1 by pi. So let us just see what is the expression for the partial sum. So the partial sums are SMF is equal to integral dmt. Okay, so we are going to put t equal to 0, and therefore you get integral fs dm of minus s, but dm of minus s is the same as dm of s, and therefore we have phi n of is nothing but integral minus pi to pi f of t dn of t dt. Therefore mod phi n of f is less than or equal to, I can pull out, take the modulus inside the sign, pull out the norm of f, that is a maximum. So I get integral into 1 by 2 pi minus pi to pi mod dnt dt. Okay, so this implies that norm phi n is less than or equal to 1 by 2 pi integral minus pi to pi mod dnt dt. So now we want to show that it is actually attained, so that this the supremum will have to be attained. So we have to find a function or a sequence of functions for which it will actually go to this optimal value. Okay, so now for that you let En equal to set of all t in minus pi pi such that d and t is non-negative. So if you draw the graph of d and t, you might have seen it in Fourier series articles or even covers of books which are devoted to Fourier series. The Dirichlet kernel, or even for instance if you have seen the journal Resonance, you will have it in the logo of Resonance. It's a function which goes like this, sort of decays out, okay, so it oscillates a lot. Okay, so now you define fm of t as equal to 1 minus m times distance of t from En by 1 plus m times distance of t from En. So you have modulus of fm is less than or equal to 1. So norm in L infinity is less than or equal to 1. So you can say norm f infinity is less than or equal to, sorry, not t, it's 1. Okay. Now I claim that fm is also in C periodic minus pi pi. Why is this so? So that means we have to show it's well, it's continuous, no problem, because the distance function is a continuous function. You have seen this in metric spaces. Distance function from any set is a continuous function, and therefore this is a continuous function, and denominator does not vanish, sum of two non-negative quantities. Okay, so why is this 2 pi periodic? That means you must show that at pi and minus pi they take the same value. In fact, this is symmetric because the set E itself is symmetric. Dn is a even function, so En is a symmetric about the origin. So En is a symmetric set about 0, and therefore you have that Fm. So since you have that Fm is in fact a periodic function. Now what does Fm of t if t belongs to En? If t belongs to En, d of t En is 0, and therefore this is equal to 1. And if t belongs to En complement, then I can divide through it by m and let m tend to infinity. So fmt converges to minus 1 if t belongs to En complement. Therefore, by the dominant, so what is the limit function? Pointwise it goes to the function which is plus 1 on En and minus 1 on En complement, and the integral is dominated by dn, which is an integrable function. Therefore, by the dominated convergence theorem, so what is phi nf? It is here. So mod, if you take the mod, you get mod ft and mod dnt. Mod dnt is integrable, and mod ft is less than or equal to 1. Therefore, we can apply the dominated convergence theorem in this proof, and therefore you get, by the dominated convergence theorem, you get that phi n fm converges to 1 by 2 pi integral minus pi to pi mod dnt dt, because where En is positive, dnt is positive, it goes to 1, it is already 1. When dnt is negative, it goes to minus 1. So everywhere you will just get the modulus, and therefore you have a sequence which goes to the supremum, and therefore this is in fact the norm. This completes the proof. So now let us apply this to the space. So take the space V equals C periodic. But then what do you know? We have that norm phi n tends to plus infinity by the proposition. This is the norm, and by the previous proposition it tends to plus infinity. Therefore, there exists a dense G delta set in V That means it's a dense set of functions. Okay, we have CV is a space of functions, so there's a dense G delta set in there such that for every F in that set, we have that Sn of F at 0 diverges. That is, Fourier series diverges at 0. So there is a huge set of continuous functions which are 2 pi periodic, such that at the origin you have that this Fourier series is divergent. Okay. Now we could have done this, we can do this, do the same thing for any point x in minus pi. 0 is not sacred. Okay, so you could have done it for any point in the interval. So we now call Ex is the dense G delta set of functions in C periodic minus pi pi such that the Fourier series diverges at x. So now you take xi, a countable set of points in minus pi pi, and you write E equals integral I equals 1 to n E of xi is contained in V, and this is also, so by Bayer's theorem, Bayer corollary if you want, E also a dense G delta set. Now for every F in E, the Fourier series will diverge at xi for all I. So you define S star of Fx equals mod sup over n, sup over n mod SNF at x so we have that set of all x such that S star Fx equals plus infinity is a G delta set in minus pi pi for each F. Because what is this? This is nothing but S mod S star F bigger than n. That's a continuous function. That's the intersection of open sets, just as we had in the proof of the Banach-Steinhaus theorem, and therefore it's a G delta set. Now choose xi dense in minus pi. So in fact you can just take the rationals, for instance. So you have a countable dense set. So then each of these S star F is also be dense. Therefore we have the following proposition. So E contained in V is a dense G delta set in V such that for all F in E, the set QF in minus pi pi, where the Fourier series diverges, is a dense G delta set in minus pi pi. So, and we saw a corollary of Bayes' theorem which says if you don't have isolated points, so in C periodic you don't have isolated points, in minus pi pi you don't have isolated points. So if you don't have isolated points, a dense G delta set has to be uncountable. Therefore, there exist uncountably many 2 pi periodic functions for which each of them the Fourier series will diverge at an uncountable number of points. So, this really, I mean the Fourier series convergence point wise is not at all something which you can take for granted. Okay, so that is, everything comes from Bayes' theorem and application of the Banach-Steinhaus theorem, and so this is an application. So, next we will look at some other theorems which in Banach spaces, two very important theorems which are again consequences of Bayes' theorem.